Hi, and welcome back to another reading of our book, Quantum Atom Optics, Theory and Applications to Quantum Technology. So in the last video, we were talking about Fock states. So that was section 1.3. And what we were doing in that section, so let's just go to the page there. Right, in that section, what we were doing is to write down all the possible states that you can have of a many boson system. So, for example, if you had, say, this harmonic potential here, and we were just looking at this ground state, so this would be the lowest energy state of that harmonic trap there, then if you had, say, a many boson system, then this state could be occupied by potentially many bosons. So we learnt how to write that down. So this AK operator denotes one atom in that spatial state. So I've labeled it by K here. So the spatial wave function is psi of K. And then if many of these atoms occupy that same spatial state, then this would be the type of state that we'd write down, and we talked about how to normalize the state properly and so forth. So what we're going to do now is to generalize this to the multimode case. So in this case, we're not just going to look at the lowest energy state here, which was the example that we looked at in that last section. We're going to look at basically all the different spatial states, because a particular atom, there's no reason why it has to occupy only this ground state. Of course, it could occupy any of these spatial states. And then if you've got multiple atoms, then this could be distributed in all kinds of different ways. So here we've got, say, 2 atoms in the ground state, 1 in the first excited, 1 in the second, and 3 in the third excited state, just for example. This is the situation for fermions. So for fermions, you cannot have this multiple occupancy. So instead, we have fermions, and they're in different states. So in this sense, they're distinguishable, and they are occupying this particular configuration. So how do we write down such a state that I've sort of pictured here in 1.2a? Well, you simply define different bosonic operators. So for each level, each spatial state, which within that state, the bosons are indistinguishable. So we would write simply like a Fock state for each of these levels. So in this case, there would be something like, let's get the pen here. So for the example that I got here in 1.2, I've got 2 atoms in A0, and 1 in A1, 1 in A2, and 3 in A3. And then we've got to normalize this whole state properly. So to normalize this state, we need 2 factorial. Normalize this one, we need 3 factorial, so forth. So that would be an example of that one. So we simply multiply successive bosonic operators, and that gives us the total Fock state, the multimode Fock state of that system. For fermions, it's similar, except that you do not have the possibility of having more than one. So either 0 or 1 occupancy. And again, so Pauli exclusion principle. So that's the state that we can write down. But what about the Hamiltonian itself? So how do we write down this many particle Hamiltonian? So, in first quantization, you would simply label each different atom by a different variable, like x1, x2, so forth, and that would be the coordinates of each particular atom. And then at the end, you've got to symmetrize or anti-symmetrize the wave function. But in the second quantization language, there's sort of a much more elegant way of doing that. So we can write down the total Hamiltonian of this multi-particle system in this way, where we have H0. So this was given by the, this is just the single particle Schrodinger equation. So if we go all the way back to 1.2, so let's have a look at that. Yeah, so this is just our usual Schrodinger equation. And to generalize this to the multi-particle situation, you simply have bosonic operators which run over all space, and then this x variable is the same variable as in the x in the single particle Schrodinger equation. So by doing this, we can actually write down the Hamiltonian of arbitrary particle number system. So this, in this formulation, the Hamiltonian works for one particle, two particles, or any number of particles that you like. So how does this work? So, or how do we know that this actually should give the correct energy when you say take expectation values? So, for example, because we actually know what the eigenstates of this Hamiltonian are, well, say it's a harmonic potential, so you diagonalize the Hamiltonian in the usual way, just using standard quantum mechanics, and then so these are the single particle wave functions that you have. Then we can write a complete basis in terms of those functions, because all these states are orthogonal, and so we can actually expand this annihilation operator, which is acting at position x, in terms of these eigenstates. And because these are now in terms of these eigenstates, we can actually simplify this Hamiltonian, and it becomes much more obvious that this is the correct Hamiltonian for the multi-particle system. So for the A dagger, it's simply the complex conjugate. And so if you substitute these into there, then what you find is that the Hamiltonian can be simplified in this form. So, okay, so let's just do that. So we have H0, so dx, and then we're going to substitute say this one, 1.33, into the formula. So this one is going to be K, just erase that. Yeah. Psi K star X of A K. And then we've got the H0 of X. And then we substitute this one into the formula, so we better put a different label on it because this is a different variable. So this is K prime. This one is still X because that X is the same as that X. And we've got a K prime. Okay. And then we can interchange the order of the sums and the integrals, because sums and integrals, you can do that. And so let's just put some of these operators out here first, and we've got the integrals, and we've got psi star x, h0 x, and then psi k prime x, like this. So I've just sort of rearranged the order. Now this part, we know what the Hamiltonian does when it acts on here. We know that it just simply gives the energy. So let me get the right variable names. So when H0x acts on that, this simply gives EK prime times by the wave function, because this Hamiltonian acts on this S wave function, and this is the eigenvalue. So let's go ahead and plug that in. So it's K prime, AK prime, integral K star X. We've got this eigenvalue. And then because this is just actually a constant, this can come outside the integral here. And then we just got our orthogonality relation, which is delta K prime. And then so one of these sums collapses. We've got this EK here, and we've got the A dagger K, and this thing is what we defined as N of K. Okay, so this is our definition, EK, NK. So basically what this says is that the total energy, the total energy of the system is the number of particles, because this is a number operator, multiplied by the energy of that particular state. So for example, if this state here had an energy E0, E1, and so forth, then that would be basically the states that you have. That would be the energies of those states that you have. Okay. All right. So we've got a bit of a kind of a bug here. So let me just try and rub some of these out. Okay. Okay, now we're back. All right, so that's how you get this Hamiltonian form here. And then if we want to write down what the total energy of the system is, then you can simply add up the particle numbers, as I was saying. So in this case, the difference here between the large NKs and the small NKs is that here, this NK here is an operator, whereas these things are the actual particle numbers. So the little n would be like the specific values of these atomic occupations here. Okay, so this would be the energy of some arbitrary configuration. So here we've got some particular configuration with particular occupancies, and that's how you would write down the total energy. And if we wanted to write down what the minimum energy is, then of course it's kind of clear from here that if you say had n atoms and you wanted to find the minimum energy configuration of all this, then of course you would put all the atoms in the lowest energy state. So that is basically just the content of this equation here. And for fermions, because you can't put all the atoms all in the same energy state, what you need to do is you say you had n atoms, you would first put it in the lowest energy state, because that's obviously the optimal configuration. And then the second atom you would have to put in the second lowest energy state, the third atom you put in the third lowest energy state, and so forth. And so this is, there's no other configurations that are available to the system, and so you have to fill the energies in this way. And so for fermions, that happens to be the lowest energy. So obviously for fermions, you tend to actually get much sort of higher energies because of this Fermi exclusion principle. Okay, so that's pretty much the content of this section. Now, as for these exercises, I think, so 1.32, this one is to basically derive this relation by inverting the relation that we had from before. So, okay, so let's do that. So let's look at 1.7 and then essentially invert that relation. So 1.7 was this particular relation. So basically what we want is a relation in terms of A of k, not in terms of A of x. So in this case, what we want to do is we basically multiply, okay, hold on. So we multiply equation 1.7 by psi kx, and so when we do that, I think we need to multiply by this, we need to put a label x prime, because this is an integration that already involves x, so we better put a different label on it because otherwise we don't want to be adding any new variables over the integral, right? So we multiply this one, and then we sum over this variable k, and we can choose that k to be the same as that k. So if we do that, then what we get is, so k, a k psi k x prime, and then we have to do the same thing to the left-hand side. So we got sum k psi k x prime integral dx psi k star x a of x, and again we can interchange the order of the integrals. So let's put the dx outside here, and so we've got sum over k psi k x prime. Okay, whoops, this one has no, whoops. Yep, this one has no k prime, and this one is a of x, and this stuff here is again, because of the completeness relation, we can write as delta function x minus x prime, and then so this becomes ax prime, and so we can invert this relation where we've written ax prime in terms of the ak operators, and so that basically gives us this relation that we started off with, or that was given in this equation here, 1.32. Okay, and 1.34 I think we did. So basically trying to get 1.34 from 1.31, we already did that one, and then verifying 1.36. Yeah, so I think this one is relatively straightforward. You simply apply this n of k operator. So this is a lot like what we did in the last section, where we have ak dagger ak, and then so when we have ak dagger ak with a ak dagger to the power of, say, nk over here, then what we do is you just commute this operator through n times, and then you get a factor of n. So when we do this, actually we'll have a lot more different variables here, but all these other variables commute, so you don't really have to worry about them. Okay, so I hope this is a little bit helpful to understand this section. If you have any questions, then feel free to comment below. And thanks for watching. And if you found this useful, then please don't forget to subscribe to the channel. Okay, so see you next time. Bye.